Welcome. Today we're here to discuss the functionality of a gasket. We're not here to sell gaskets. We're not here to talk about gasket materials, types of gaskets. We want to know where it goes and what happens to it as it goes through the cycle of doing its job of sealing. What is a gasket? A gasket is a material or device that forms a static barrier between two relatively stationary assemblies, normally flanges, could be a cover on a vessel, could be a boiler door, handholds, manholes, usually clamped together with a threaded device, studs, bolts. Those are the materials that are required to create sealing stress. Now when I use the word sealing stress, that's the compression load on a gasket itself. When I talk about pressure, it's going to be the internal pressure. So those are the two things that I wanted to point out at the beginning. The junction formed by a gasket, mating flanges, several fasteners, usually ends up being quite dynamic. Expansion and contraction from heat and cold, water hammers, vibration in the line. Hydrostatic end force, which we'll talk about later, is the actual pressure, internal pressure, trying to open the two flanges apart. All these things that you don't see. And the gasket has to put up with all of those things. And of course, when there's a failure, when there's a gasket leak, it's the gasket's fault. Nothing to do with the bolts or how you installed it or whatever. Today we're going to talk about those different things. First of all, here's a picture of the two flanges. It's a spring device. The internal pressure is trying to expand, open the flanges. The bolts are trying to close the flanges. Bolt being spring itself is susceptible to relaxing and movement all in itself. So when we get into washers, bolts, nuts, these are all the things that are affected to create the load on the gasket, the sealing stress that we're looking for to achieve the gasket's main job. So we're looking at a flange at the moment. I just wanted to go back and talk about a flange. What's a full face? What's a ring type? Is flange thickness a problem? Where does the gasket go? A ring type gasket is designed, and I'll make the point right now, that gaskets are scientific. Gaskets are all engineered, they're all specified. You don't have to worry about any swaying. If it's this, it's this. If it's that temperature, it's that temperature, and this is the effect it'll have on the gasketed joint itself. In this case, I'm showing a raised base. The ring type gasket that you'll hear is engineered or designed to use the inside of the bolts to place it on that raised face. A full face gasket goes the entire full face. That's usually in a rubber gasket or in a plastic flange where you'll have lower bolt loads, and you need to ensure that you don't get a cantilever effect. If you put a ring type gasket in near the ID of the pipe and the area underneath or in between the flanges where the bolts are is empty, you're going to pull from either end and cause breakage, essentially, or what they call flange rotation or warpage. So that's the two different things. Again, the specification used to be a 4-inch pipe had a 4-inch ID gasket. Now it's 4 5/8. That was designed again to ensure that we don't get penetration into the line. The tolerances between the bolts and the bolt circle, the bolt holes, will allow, in a horizontal, for example, the gasket to drop down and actually protrude into the line and create all kinds of turbulence, or break off pieces of gasket and you find it in your Coca-Cola later, something to that effect. Okay, so the main point of what we're talking about today is the flanges, is the bolts, nothing to do with the gasket. So when you're choosing the right gasket, you gotta have the right size. I just alluded to the fact that a ring type and a full face have different dimensions, different one has bolt holes, one doesn't. But they are designed by engineers over the last 100 years to be this for that flange, this for that flange, and it doesn't change. So size, you need to know the class of the pipe, 150, 300 pound. Again, go back to the ASME B16.5, which regiments all the gasket dimensions and so on. It'll tell you exactly how big that gasket is. Temperature, extremely important. Temperature, of course, they all have limits. I believe in safety factors. If it's 500 degrees, the gasket's good for 500 degrees, well, don't use it. You need to have, you're going to get variations in a line, you're going to get equipment holding up and pressure building up. As pressure builds up, temperature goes up and so on. Always build in safety factors on temperature. Application is what we're talking about. Application is not the temperature, the pressure, the media, etc. We're talking about how many bolts do you have, what are those bolts made of, are they lubricated or not, etc., etc. The actual junction of the gasket. Media, of course, is the chemicals, is the water, is it sulfuric acid. Concentration of that is very important. I'll repeat it a couple of times, but sulfuric acid at 100%, you can put your hand in. At 96%, with the 4% being water, it'll eat your hand off. So you have to, concentration and what else is in the mix is extremely important to be compared to whether that gasket will do the job or not. And pressure. Now I'm talking internal pressure. So we need to, of course, know how much force is trying to blow that gasket out from between those two flange faces. A gasket's main function is to fill the imperfections in the void of a flange. Normally flanges are grooved, a concentric groove or a phonographic groove. They're there for a reason. Flange surface finish are designed so that the gasket can grab onto it. So a gasket's job is to compress enough to fill the voids in the flange and then stay there, create that static barrier that I was talking about. Different measurements of flange finish are rated in RMS, which is root mean squared, or AARH, which is arithmetic average roughness height. And basically it's the distance between the peak and the valley of that groove, or the pitting in the flange. How deep is it in microinches? So a standard gasket will be 250 RMS flange. It has enough depth and enough material to go and grab onto that so that that internal pressure I was talking about before doesn't allow, it doesn't blow out the gasket. The gasket's actually grabbing onto the surface of the flange, and that's how it's designed. Gaskets are also designed to densify, to compress so that, I'll take 2 steps back. A compressed sheet, for example, is a mixture of fiber, rubber, solvents, becomes like a putty that is formed into a sheet on a calendar. Therefore, there are tunnels or capillaries of leakage paths through that material itself. When you compress the sheet down, you're trying to close those capillaries or tunnels of leakage, and you achieve it to a certain point. Asbestos, of course, was a rock, so it took a lot of load to close down those capillary radiuses. The non-asbestos is more rubber, therefore the sealability or the resistance of leakage through the gasket itself is greatly reduced. And we'll talk about that. How do we test for that? How do we know if that gasket's hard or soft or whatever? Here's where we go. We talk about lab and QA testing. We have tensile strength, stress relaxation, excuse me, hydrostatic pressure, elevated temperature, sealabilities, density checks, hot compression. The difference between American and European testing and design is extremely different. The Americans have a tendency to have a broader range, and I don't like to demean, but a lackadaisical attitude towards the way to present the product and its abilities, whereas the Europeans, driven by the Deutsche Industrie Normen, are extremely, extremely technical. And we'll see the difference between the two. Basic tests, compressibility and recoveries, and OEM testing. You might have a customer saying, I need it to be, to go into oil and swell this much, or it needs to resist this kind of temperature for X amount of time. We could do those kind of tests as well. Some of the test procedures, as I had mentioned, everything is written down. The Bible for gasketing is the ASTM, American Society of Testing Methods, F-104. That's the book. So page 1 is this test, page 2 is that test, and exactly how to do it so that all manufacturers, Garlox, Klinger, Durabla, whoever, all do the same thing to their gaskets and give you a result. So you as a consumer, or you'll know what happened to it, and therefore you can compare, okay, well, if you put 5,000 PSI load on that gasket, it'll compress this much. Everybody is comparable. As I mentioned, the American view of testing and the European view of testing differs in technicality. They're all trying to achieve the same goal. A couple of the different tests ASTM do are compressibility. How much load does it take to drive that gasket into the surface of the imperfections in the surface of the flange? How much memory does it have? How much recovery will it have? That's an ASTM F36. So in the F104 book, the F36 is one page, the F37 is creep relaxation. All of these different tests are all outlined in that what we call the Bible. So here's a picture of the actual ASTM creep relaxation fixture. You'll see that it's just basically 2 platens with 4 pieces of gasket. Those 4 pieces actually add up to 2 square inches so that our load will be in PSI. You see you have your shaft and you have a pressure gauge or a torque gauge on the top. You torque it down to X amount, depending on what the ASTM F38 says, and for X amount of time, and you calculate the actual volt torque loss that has happened because the gasket has relaxed or flowed out, and that's called creep relaxation. The F36 I just explained to you was essentially a very simple test. You take a gasket, you measure the original thickness, you put a 5,000 PSI hydraulic load on it for 1 minute. And you calculate how much it compressed. Gives you an idea of how much that material is going to move, and juxtapose that against the depth of the grooves in your flange, and you'll know whether it's going to do the job or not. Recovery, same test. After that 1 minute, you let off the pressure and you wait another minute. The key here is the compressibility travel or rate is what you're looking for as far as recovery, not the entire thickness of the gasket or the original thickness of the gasket. So to say if your compressibility was 10% on a 1/8 thick gasket, so it's gone down 12 thou, 13 thou, of that 13 thou travel, how much of that came back? Normally 50, 55%. So that gives you an idea of how much spring back the basic, will the gasket do the job or not? Is it hard? Is it sponge? Or under 5,000 PSI load, it will just completely flatten out? Or is it a rock where you can't get it to move? The ASTM F37, again, I've reiterated a couple of times. This is the American version. It has 2 platens, an input for gas and an output for gas. They put the gasket onto that platen, and there's a hole at the inside of the gasket and a hole on the outside of the gasket. They don't do anything to the surface of the gasket. They introduce X amount of pressure under X amount of load, and they calculate it. The gasket will leak across the face of the flange and through the gasket, and that's the North American way, if you want to call it. Not as accurate, but when you're talking about sealability and gas permeability, it's not leakage you can see. It helps us compare materials. So it's kind of like looking under a microscope. So you can really get deep down and go, okay, I'm sorry, that guy does that in this application. That guy does that. You can't see it, but because of asbestos versus non-asbestos, we're forced to look deeper and deeper and deeper into the way that we do things. Here's the DIN 3535. It's supposed to achieve the same test, but on the right-hand side, you'll see that test fixture, and it's basically two flat platens, just like the other one, except they put a polyethylene film on either side of the gasket. So they basically gasket their gasket, and you'll see that there's a black band around the edge of it. That actually has an O-ring on the inside and creates a closed environment. So when the gasket leaks, it's trapped and it's measured on the mercury manometer on the left-hand side. The beauty of this is it will only leak through the gasket. We've gasketed our gasket. And again, if you do that to it microscopically, you're going to see leakage through that gasket itself. What does each material do? And you can compare. Klinger decided, well, that's not enough. Creep relaxation, sealability, all those good things. I want my own test. So they came up with what they call a hot compression test. And again, it's real world. You put the gasket in between two platens, you have a constant hydraulic force, which is 7,250 psi on that gasket, and you introduce temperature. You increase temperature 50 degrees per minute until you achieve 300 C, 572 F. And because the hydraulic load never changes, it's the gasket that is changing. So the thickness of the gasket is changing, and that's what the Klinger wanted to see. Not how much bolt loss, but what's actually happening to the gasket. How much is that gasket breaking down? And when you do this test, you can see, we'll look at it in a sec, how the gasket actually breaks down. You can pull it out and see the cross-sectional variance, the breakdown of the fibers, and so on and so forth. So what we're seeing here is kind of an overview of that. On the right-hand side, you see all the flanges and the piping and the valves that are put in and so on. Gasket compounds, for example, are a no-no. Back in the old days, the asbestos gaskets would stick incredibly after 2 years in a steam line or whatever. So a lot of people would put never-sees, they'd put Teflon paste, they'd put oil, whatever they wanted to, so that a year later they wouldn't have to scrape that gasket out. The problem with that is the gasket's supposed to grip on that surface, and that's why there's imperfections and so on. If you grease that, the gasket's got no way of holding on, and that internal pressure will push that gasket out of the area. That's what it is. Gaskets nowadays, primarily the compressed sheet that we're talking about, are treated with an anti-stick compound, which we'll actually see the difference cold and hot by using different compounds and the thickness decrease that is created by greasing that gasket. One of the things that we always have to deal with is pressure and temperature. Pressure and temperature, the law of physics says if pressure goes up, temperature must go down. Simple as that. Again, I'm comparing two different European and American. The Americans like to use a P times T factor. Now, P times T, or Garlock's 3,000, their Blue Guard 3,000 is 350,000. So if that's the case, and that's a constant number, they always said that non-asbestos compressed sheet was good to 700 degrees. So if it's 700 degrees, what's the pressure allowable? Well, 350,000 divided by 700 is 500. So that's the maximum pressure at that temperature. But if you've only got, well, okay, as non-asbestos evolved, they realized that 700 was a bit much for compressed non-asbestos. So they came up with a continuous operating temperature, which actually is half of the 700, is 350. That's what it'll really take. So at 350, how much pressure can we put on the gasket? If 350,000 is the standard P times T factor, it doesn't change. At 350, I can put 1,000 PSI in that gasket. The Europeans, or the the clingers of the world, like to use graphs, and not just Klinger, but many of the Europeans, even the Japanese, use these graphs of pressure and temperature, and they set up zones. So zone 1, go ahead and put it in. If you're in that pressure temperature range, no problem. Zone 2, in that green area that you see, pay attention to your loading. Have you got the right bolt torques? Have you lubed your bolts? Have you taken a look at the entire picture that we're trying to discuss today? And in zone 3, forget it. You're way out of your pressure and temperature league, and you're going to go to metal, or you're going to go to something completely different. The beauty of these two, the beauty of this is you have two graphs, one for liquid, one for gas. Two extremely important differences. If you go back to sealability, gas will leak through those capillary radiuses and leak through the gasket itself a hell of a lot easier than tar or liquid or water. So we give you two different pressure temperature curves. So these are our materials. What I'm trying to show you here is there's commercial grades, there's premium grades in everything, in rubber, in compressed sheet, there's quality, and then there's lesser quality, and sometimes you don't need high quality, you don't need that high pressure, high temperature material. How do you know the difference? So then you can take your, okay, well, I've only got this, it's a medium kind of an application. I don't need to go for that full price sheet, if you want to call it. And again, you can just run down through that. Creep relaxation, compressibilities and recoveries, sealabilities are there. Your pressure and temperature curves are very important when you take a look at those curves, because we don't have fillers or as much clay, if you want to call it, in the 4401. It's a higher quality sheet, longer fibers. It takes more pressure and more temperature. You can see, that's what we're here to talk about, is what will it do in your flanged application. The original green, I stole this from the Klinger website, going back to hot compression. So you put that gasket in, install it right, walk away, the equipment's running, the boiler, if you want to call it, high temperature, high pressure. You really want to know what's going on with that gasket. Is it going to hold up? So you take a look at the hot compression test. As I had mentioned, a hot compression test is a constant load. So we're not losing bolt torque. So if we don't lose bolt torque, and the bolts keep pushing, something's got to give. It's actually the gasket. So what we'll do is we'll go to the website, and here is the information on a hot compression test. As I had mentioned, at 7,250 PSI, we're looking at 572 degrees Fahrenheit. We increase heat incrementally, 50 degrees at a time, in a 1 minute interval. We want to show actual industrial usage. You put your gasket in, you turn on your equipment, the temperature goes up, runs X amount of time. What's that gasket doing? Is it relaxing? Is it melting? Is it holding up? We want to be able to see that before we lose a piece of equipment. So what we do is we do a cold test under that pressure, and we do a hot test under that pressure, and then we take an average. So if we do this, here's a picture of all of the different competitive materials that we tried in the same test. And this is the beauty of the whole thing. We did the same thing to every one of them. And this is the way they came up. Some are good, some are bad. If you look at sample A1 as an example, you have, we're 8.8%, the competitive product is 11.7 in cold. So just the load itself did that to the gasket. When we put on the heat, we lose 18%, excuse me, and competitive 42. And you can just look at the picture of the gasket and see how much it broke down. This material, in the overall, in the average, 48%, almost 50% thickness loss. It just crushed out. You want that gasket? No, but they all look the same. They're all the same color. How do you know the difference? Well, you can go back to ASTM, DIN, or the actual Klinger hot compression testing. Let's try this guy. In this case, we're still 8.8, so you can see the consistency. This guy's 12%. We're looking at 50% breakdown in hot. So that tells you that there's a lot more rubber in it, a lot of filler and clay, and not a lot of actual fiber. So it's breaking down. We'll take a step back. We'll look at this service questionnaire, if you want to call it. We'll start with duty, which I like very much because it's, what is the chemical? What is the concentration of that chemical? What is your temperature? That's your, what we used to call application. The maximum temperature, again, you want to use safety factors involved in that. Pressure, as I said, is internal pressure. Is it a ring type or a full face gasket? Is it liquid or gas? Extremely important. Again, we'll go back to sealability. Is it a gas? Is it going to leak through the gasket and across the face of the flange much easier? We need to know that. Our flanges, what are they made of? What is the rating? What is the pipe class? 150, 300. Again, it's all written down. If it's a 4-inch 150, it's this big. If it's a 4-inch 150 ring type, it's this big. Full face, it's this big. It's got that many bolts, that many holes, etc. So we need to have all of that information. What's the surface finish? Is it 63 RMS and I can't fill that void? My gasket can't bite on that hard enough? Maybe I need to change that. Again, it's got nothing to do with the gasket material. It's got to do with the actual flange, the condition of the flange. A good example of that is in a boiler handhole or a manhole cover. Steam pits flanges, that's why most boiler gaskets would be 1/4 inch, because the steam itself is attacking the surface and you need more meat, more material to fill those voids. So that's where we stand with flanges. They're a very, very important part. Your gasket details, are they full face, are they ring type, outside diameter, inside diameter, number of bolts, etc. We need to have all that information. We can use that, we can input that into our Klinger Expert software design program. All of those things come into play. An example, and we're going to get into sealing stress in a minute versus area, but maybe your gasket's too wide, which means that you have too much gasket to compress and not enough load to compress that much area. We'll understand that in a sec, except to say that maybe I need to add a bolt, maybe I need to redesign and put more bolts in or take bolts out because I had too much load, etc., etc. And talking about bolts, what is the bolt made of? Is it a high-end titanium super bolt, or is it a carbon steel, copper, brass, whatever? How many do you lube them? We're going to really look into lubricating the bolt, the threads, the head, and so on and so forth. So that, I did this because we want to look at, this is the whole picture. The gasket's part of it, the flange is part of it, the flange surface is part of it, the temperature, pressure, and media is part of it, the bolts, lubricant or not. Did you lubricate the faces of the gasket and therefore destroy the whole basis of gripping and holding statically in place? So hot compression testing allows us to do a couple of different things. In this case, what we did was we lubed our gasket when we said we shouldn't, with all kinds of different things. And we put it in the hot compression tester to make it move, to assimilate actual industrial usage. The first one is NST coating. NST is non-stick treatment. It's what we do to every gasket now, therefore you don't need to lubricate it. When we finish making the sheet itself, we treat it with a mica coating that takes 2,000 degrees. It's like a powder, so it will release the gasket from the face. Okay, so the difference between no coating and NST, as you can see, is minimal. So it doesn't have any real effect. But then you get into Teflon and never sees and so on. Cold, you're losing 48%. Hot you're losing 48%. Cold you're losing upwards of 30% of the thickness. That means the gasket can't grab onto the flange surface. So don't lubricate your gasket surfaces. In this, we use a 2-inch B7 stud. Now, a stud is different from a bolt in that you have two nuts turning in opposite directions, therefore the bolt stretches. It just goes one way. Whereas if you have a head of a bolt and a nut, it'll actually turn on itself, therefore your torque value is not as accurate. So here we have a 2-inch B7 stud, torqued at 50% yield. As I had mentioned, a bolt is a spring, and a spring can only spring so much before it doesn't spring anymore. So that's the way a bolt works, is that there is a minimum to pull on it, to start it, to fight back against the force, to a maximum where it finally gives up, if you want to call it that. So we're talking about 50% yield, we're starting in the middle of that. Therefore, that bolt is where it wants to be. It's at its ultimate power, if you want to call it. So if you didn't put any lubricant on this B7 stud, and it's 2-inch because we wanted to show a big number, 6,000 foot-pounds of torque at 50% yield on this stud if we don't lubricate it. Then we put some lube on the threads, all of a sudden we require 2,000 foot-pounds of torque less. That's a huge number as far as that torque is the pulling that is stretching the bolt, stretching the spring. Lube on the face only, pretty well the same idea. If you lube the entire bolt or stud and nuts and the entire apparatus, you can reduce your foot-pounds of torque required by 4,000 foot-pounds. That's how much transfer, that's how much non-lubricated bolts friction stops the bolt from doing what it's supposed to do. Okay? So very important that you do that. Stress. Yes, stress is an everyday occurrence. In this case, as I mentioned at the beginning, Stress is the load on the gasket itself. I alluded earlier to how much load on how much area. So if I got a square foot of material and I put 1,000 pounds of load on it, then that's what I require. If I have half of that material, then I probably got too much load. If I have twice that material, I may have half the load I require. So let's look at that a little clearer. Force is what we use those bolts to create. We're trying to create a load on a surface area itself. In this case, our gasket is 49.7 square inches of material. It's the area we're concerned about. So we're taking our load, which is created by, in this case, 12 bolts. And each one of those bolts, at 50% yield, if you want to call it, it's giving me 25,000 pounds of weight on that gasket. So 12 times 25,000 pounds, I've got 300,000 pounds of load on that area of gasket. That's what I'm worried about. So if I've got 49.7 square inches, divide that into my total load, I've got 6,036 PSI load, pounds per square inch of material. As I had mentioned before, what if we take, we don't have enough pounds for the square inches? Well, we've got to reduce the size of the gasket then. That contact area has to reduce because I've only got so much load. Or vice versa, I could add, if I had a bigger area and I don't have enough load, I can add a bolt or design a bolt in. You know, we can't just add a bolt as I mentioned earlier. But so if we look at that whole spectrum, now we put a gasket in. Tensile strength, we didn't touch on really during the testing portion, but it's done by pulling at the end of the material to see how strong it is axially. That tells you whether the pressure will blow it out or not, whether it's strong that way. So we put the gasket in, we start at 0 PSI. We need to have a minimum amount of load, whatever it is, to get the gasket to move, to start to crush it, to get it to fill the voids and the imperfection in the surfaces of the flange. But minimum doesn't mean that we've gotten anywhere near fulfilling all the other needs, closing the capillary radiuses, strengthening the material, and so on. And then you can get carried away, and the crush point in this scenario is 25,000 PSI. That's what will kill the gasket, finally just destroy it. We have compression from the flanges, we have the internal pressure trying to open up the flanges. So we have all these different characteristics that we have to account for with the bolts and so on and so forth. I mentioned earlier hydrostatic end force. That is the effect of the internal pressure trying to open up the flanges. In this, you see the bell on the top. That's the actual tester. That's how they do it. They make a great big bell and they put internal pressure, and using that bell on the top gives you a pressure, gives you a backstop to see how much of your internal pressure is pulling those flanges apart. Just to give you an idea, that's why there's a bell on top of this. It's called hydrostatic end thrust. That's how involved it gets. It has to do with the area of the pipe, how much pressure is within the pipe, and so on. We're not here to engineer or re-engineer anything. I'm just here to tell you that I have a clamping load, compressive load. I have my flanges trying to open up because of HET. And all of a sudden, I've only got 5,350 PSI on my gasket, not 6,000. I've lost 1,000 pounds. So that's going to be a big deal. You have to adjust, bring your yield from 50 to 60, put more torque on your bolts, stretching that, but then of course you have a limit. There's a limit on the compression on the gasket. There's a limit on how far you can stretch the bolts before things come apart. When we talk about bolt grade and quality, it can be just a carbon steel bolt with a little bit of lube on it. You can have titanium bolts, you can have high temperature Inconel bolts. The standard in the industry is basically B7s. They're an alloy type bolt, but all of these are listed on this chart. You have a minimum yield strength. That's how much torque you have to put on it to get it to start stretching. And then there's a maximum where you'll overstretch it. Here's a better example. There's a gasket, there's a bolt, or a stud in this case. And look what happened to the spring that it was. They over-torqued and over-torqued and over-torqued, and they just pulled the whole thing apart. It takes a lot of power. It takes a lot of foot-pounds of torque to be able to take a piece of metal like that and stretch it. So that's how much force we're talking about here. And if you get to that level, we have a problem. So this is strain, and strain is essentially the difference in length after you've pulled on the spring and where it ended up staying. So it gives you an idea of how much load you're putting on it, whether you have too much or too little, and so on and so forth. So finally, we end up with a total calculation. What were we talking about today? Well, we're talking about a gasket, the size of the gasket, the bolts, how many bolts, what are those bolts made of, what lubricants did we put on it, did you lubricate it, what coefficient of friction does that lubricant have, how much internal pressure do you have, is it liquid, is it gas, and so on. All of this is accumulated right here. This is Klinger Expert software. I have told it that I want to start with B7 bolts. I've told it as a default I want 50% yield. So when it does any calculations, it's going to start where I want it to be, so I don't have to keep typing in all the time. So in this case, we have 1.5 inches, 150. It's got 4 bolts. I've told it to be B7s. I've told it to have a 0.10 coefficient of friction. That is low. A standard coefficient of friction would be 0.14 or 0.15. Any of the lubricants that you're going to use to lubricate those bolts on the bottle or on the tube, it'll be marked what that coefficient of friction is. So that's where you can reference that information. How many bolts do I have? What are they made of? If you look at the top right, I have 72 degrees or ambient. I have 1 atmosphere, 14.7 psi. It's air, just to give you an idea. And in the middle are the numbers that you're looking for. It's very difficult. Again, this is the European way of doing things, so they get a little technical. So they have BO and VU, but what you're really looking at is BO is that crush point, the maximum you can put on that gasket before you kill it. In this case, it's 11,000. I can't see the number completely, but your E minimum is that number I gave you previously on the graphic at 1100 psi. That's how much to get the gasket to move. All the bolts, all the load, all the foot pounds, all this and that and this, and coefficient of friction and lubrication says that if I do that, I've got 8,000 plus load. And it puts me, if you look at the two graphics, the one on the left is installed, the one on the right is after operation, because you have creep relaxation, you have movement of the gasket and so on. You want to be in that green, but if you look on the left-hand side, you'll see your E min. If you did that, you're in the yellow, you're just starting, you're nowhere near loading that gasket. Your BO, of course, is the other end of the scale where you would store the gasket. And your E min, your 8,000 foot-pounds of torque at 50% yield on that bolt, et cetera, because it all works back and forth. I need more load, well, I'll up my yield, I'll torque the bolt a bit more, and up to 100% yield, right? Before I stretch it into what that picture before showed you of the stud that's extended. all of that to say, this is the way that all of these things interact with each other, and that's what we wanted to talk about today. We also have metallic gaskets. If you're moving on to the yellow portion of our pressure temperature graphs, well, this may be someplace we want to go. Compressed fiber is what we've been talking about. PTFE gaskets, joint techs, expanded Teflon, modified Teflons. These are all the effects of what happened when we couldn't use asbestos anymore. So all of that to say, I'd like to thank you very much for your time. It's important to look at the junction of the gasket, what's going to happen to the gasket, not just the gasket. So when you're looking at price versus value versus quality, maybe it's not the gasket. Maybe it's what you did to it. So thank you very much for your time, and we'll see you again sometime.